This week, we will talk about logistic regression. Um, so let's go ahead and start. So what if the response variable we're interested is a qualitative variable, which means it's a categorical variable or binary, like 0 or 1? Yeah, so for this case, what shall we do? So for response variable being qualitative, we normally call this regression being classification. So formally, we see the process of predicting qualitative or categorical response is known as classification. And so intuitively, it can be sort of a classifying observation. Like since you are assigning it to a category or one class. And most of these methods will first predict the probability of each of the categories. So the category itself as a qualitative variable, but the probability now becomes quantitative, right? And we use this probability to like assign the classes, to make the classification. So with this, like we predict the probability that we can still use the old method that we learned all about regression methods, regression models, either like simple linear regression or multiple linear regression, depending on how many predictors you have. But the only difference is that the response, the output for this logistic regression is this probability of y being like one of the category. So for here, probably for here, y equal to 1, we're pretending that it's a binary case. We have binary response. Oops. Yeah. And well, the ability of classifying observations, doing this classification, will dramatically expand our ability for data analysis. Just think about how often we would encounter this classification problem. A couple examples here, like a person show up to your emergency room. We're pretending, like you're pretending you're a doctor, and their symptoms can be from one of 3 conditions. So a categorical response variable. And what do they have? Trying to diagnose what problem they have depending on their symptom. And another example is that my online bag needs to determine whether or not the purchase I just made was fraudulent based on the information like the IP address and the past transaction history. This is a very common case where you will need to do binary classifications. And which of the DNA sequences are disease causing and which are not. So again, you are deciding something is or is not disease causing in this case. So in all of these cases, the outcomes are categorical, qualitative. So they are not always continuous numbers. That's why we need this logistic regression. So, well, the data for the intro to classification we will use across like this lecture is a simulated default data set. We're predicting whether an individual will default on their credit card payment on the basis of annual income and monthly credit card balance. So we know the balance and we know the income, and we try to predict whether this person will default or not. And we will learn how to build a model to predict the default being y, for any given value of balance being our x1 and the income being our x2. And because y isn't quantitative, it's binary, default or not, right? So we cannot use linear regression. Instead, we will use logistic regression. Well, the good news here is that this example or the data is exaggerated, have an exaggerated relationship for demonstrative purpose. So you will see there is a clear pattern for us to do this logistic regression to make our prediction. And for this particular data set, the default rate is about 3%. So it's only, it's very small number of like very small like percentage of the data set have the result being default. So in this plot, only a fraction of the non-default is plotted. So this is very common encountered in industry. Like the true cases where in our example is a default is really small. For example, for the credit card default, payment defaults are like fraudulent transactions. We have very small percentage of being like the truth default or fraudulent transaction. So in that case, normally people would just use something like downsampling or like upsampling, depending on which one you focus on. But for this one, we're downsampling the non-default so that the data size for default and non-default is comparable. So that's kind of a pre-processing of the data in the real world when you have a raw data set. But here, let's just look at this pre-processed data set, and we plotted the income versus the balance and labeled the whether it's default or not by color, and also the characters. And the orange is the default and the blue is non-default. And we can notice they are relatively comparable in terms of the sample size, but that's not that important for this case. Like for the illustration of this logistic regression. But more importantly, we are trying to look for which one influenced the default more obviously. So we have this default and non-default, two box plots for comparison here. It's clearly that a higher balance will result in a higher chance of default, right? But in terms of income, well, whether it's default or not, seems not affected much by the income, just by looking at this box plot comparison, right? Because like whether or not being default, kind of fall in the similar range of income, so not very easy to distinguish in terms of income. So well, before we go into the logistic regression, you might naturally have this question: why don't we just use simple linear regression or multiple linear regression? Well, if you consider the case where you have three outcomes, blue, green, or purple, and you encoded them to 1, 2, and 3, and fit a least square model to predict this. But your 1, 2, and 3 is implying or ordering, but actually like the blue, green, and purple, there's no order for it, right? Even if you encoded, you put them into numbers, seems like they are no longer qualitative variables, but this ordering kind of does not make much sense for this color category. And this like 1 and 2 is that green is halfway between blue and purple. Like what if you put them in a different order? So the order is misleading in terms of determining this color. And what if when you do prediction, you get something like 1.25? What does that mean? So, well, it's probably blue, but also might be green. So in this case, it just does not make sense if you do something like this, right? Well, if you do have variables that take a natural order, and you feel like the gaps between the categories are similar, in that case, you can categorize them as small, medium, and large, and you know like the gaps between these 3 categories are similar. Or you can just name them as mild, moderate, or severe. So it's acceptable to do this. Well, in this case, if a fitted value of 1.5 would mean something just is not just nonsense, because like 1.5 might be like halfway between mild and moderate, while comparing to halfway between blue and green, relatively. So this is acceptable if you know like the gaps between the categories are similar. And you can have binary response, right? In which case you can use dummy variable approach from before. That when dummy variable approach is that you name y equal to 1 if, for this example, if it's seizure, you see y equal to 1. And if it's a stroke, you will see y equal to 0. And then you fit a linear regression model and to this response y, and you can do predict if y hat, the predicted y greater than 0.5, you would say it's a seizure. Otherwise, it will be a stroke. Well, this 0.5 is just commonly used cutoff. You can always use a lower number or higher number depending on if you are more preservative. Well, yeah, so more generally, that we will use logistic regression to predict the probability, to build a model for that data set, like we just mentioned. Well, when we use logistic regression, it can show that this x beta obtained from the linear regression is actually an estimate of the probability being seizure given x. Well, if you really use this x beta to estimate this probability, it can actually give you something outside 0 or 1, right? So in that case, how do you get interpreted? How do you interpret them as probabilities once it's outside 0 and 1? And also, so for this case, it only works for binary classification. So we'll actually need to learn some actual classification on general method, classification method for more general situations. Yeah, here is another thing to kind of demonstrate why this linear regression not working for us. So for this default data set, and I have this probability of default on the y-axis and the balance on the x-axis. And 0 means non-default, 1 means default. And this orange bars are indicating for different balance, indicating a default or not. This is basically a plot of your data. And if we use linear regression, just regress this probability on balance, you will get this blue straight line, linear regression. Yeah, as I said, the orange ticks are the 0, 1 values for no or yes default, and the balance variable is on this x-axis. And if you look at this simple linear regression line, some of them are predicted being negative. Well, hard to interpret, right, in terms of probability. And comparing this with a logistic regression. So for the same data, if we do logistic regression to do the classifications, we will get this blue curve here, right? This looks much nicer because all the probabilities lying between 0 and 1. And it gives us idea like how likely it will become default from non-default, like at what range, right? It's getting really steep. The probability of increasing is getting really steep when the balance is around this range, right? Yeah, you see the effect of comparing this logistic regression with linear regression. And yeah, let's talk a little bit more. So for this data, this logistic regression model gives the probability of default given the balance. So given the balance, the probability of default. Given this balance, the probability of default going like 1.5. And it's shortened as probability given this balance, or we normally say px. And these values are within 0 and 1. And we can, with this probability, we can make predictions for any value of the balance. Once the balance is given, we can predict this probability. And you might predict default equal to yes for anyone for which the probability greater than 0.5, right? For this area. If you decide your cutoff being 0.5, if you want to be more conservative, you can choose a different threshold. Okay. So this cutoff is subjective. Well, let's like seriously talking about this logistic regression. How did we do that mathematically? Now we want to model this px, like the probability of this x is the balance if you think of that example. So that's your predictor. So which is actually the probability of y equal to 1 given this x value. So we want to model this probability. In going the linear regression route, we want this probability being a linear line. Well, if we do this directly, it will give us a negative probability of default for a small balance like small x. It can go negative, right? If we predict for large balances, we can get value greater than 1. We saw that previously. And to prevent this, we model this probability with actually is a function that only gives values between 0 and 1. So we want this probability being a function that's with the results within this 0 and 1 range. And the function we use for logistic regression is this logistic function. It's just like this. So this value, it will always be from 0 and 1. It can be yeah, from 0 to 1. Yes. Well, let's come back again to this plot. So, and this logistic function, I mean, just this thing, this function, will always give you a S-shaped curve with respect to x. In this case, is a balance. So for low values, we predict the probability is close to, but never below 0. And similarly for high values, close to 1, but never above 1. So no matter what value you have for x, and we want to predict it for, and we would get a valid probability with this logistic function. Okay. And well, one important concept in logistic regression is called odds. You might heard about this before, or very often heard about what is the odds of something happen. So this is our logistic function, and transforming or like rearrange this thing, we can get this px over 1 minus px is just equal to this exponential function. And actually, this part, like p over 1 minus p, is called the odds. And this odds can be any value between 0 and infinity. Well, what does it mean, the odds? It is the probability of it happening over the probability of it's not happening, 1 minus p here. So for the odds, when it's close to 0, it means very low probability of it happening, right? And a very large number means a very high probability of it happening. So example here, if the probability equal to 0.1, then the odds would be 1 over 9. So this will consider being a really low probability of something happen. Comparing to when the probability equal to 0.9, and then you got an odds of 9. So this is a much higher probability of it happening. So this probability and the odds kind of goes hand in hand, but probability would always be from 0 to 1, but the odds can be from 0 to infinity. Okay. Yeah, more importantly, we remember what's the definition of the odds and the relationship of the odds with this, for example, your x and your coefficients. Yeah, logistic function, you're supposed to know. Okay, another definition called log odds, or we say logit. When we take the log of both sides of this thing, we get the log odds, and on this, well, on the right hand side, it becomes a linear line, right? So we have designed it so that the log odds is linear in x, and change the x by 1 unit. Change the x by 1 unit will change the log odds by beta 1. Or multiply the odds by e to the power of beta 1. Remember, there's a log here. So this interpretation of this beta 1 in this logistic regression changed comparing to like linear regression, because we are modeling this log odds, right? So because we do not have the linear relationship anymore, the change in px from a change in x will depend on the current value of x. But we still have the positive and positive relationship. So a positive change in x will cause a positive change in px for a positive value of beta 1. So the direction will be still the same, but like the exact interpretation would be in terms of the log odds. So we preserve the relation because this is because of this transformation of the log. Okay, so this is basically the idea behind logistic regression. We are regressing this y, your logic on x. So we need to estimate the coefficients of this linear model, beta 0 plus beta 1 times x. We want to estimate beta 0 and beta 1. And in this case, we could do a nonlinear least squares, but fitting the model with maximum likelihood is more general. So, and it has better statistical properties. For example, a maximum likelihood estimator is consistent, and consistent is defined as the estimate would converge to the true parameter as we have more and more like sample size, as the sample size goes to infinity. Yeah, so we'll generally just use maximum likelihood to do the estimation. Well, some reminder, a refresher about maximum likelihood estimation. To fit a MLE, so MLE is short for this, maximum likelihood estimation. You are literally maximizing the likelihood function of the data. And the likelihood function is a statistical model based on the probability of the situation. So you have your likelihood function. And you can think your likelihood as the probability of your sample of data happens given the model and the coefficients, basically the whole model. And you want to maximize this probability by tuning the parts that we can control, which is the coefficients inside the model. So this is the basic idea of the maximum likelihood estimation. And well, here for logistic regression, we're working with the binary outcomes. It's either in the group or it isn't. And we want to find the estimates of beta 0 and beta 1 so that this probability is as close as to 1 when the subject I is in the group. Well, we want our prediction as close as to the truth, right? And we can write the likelihood like this because we have I from I equal to n, like go over, like we have n data points. The likelihood is about the data given your model. So this is the likelihood, and we choose our coefficient, which, well, the coefficient is actually within this px thing. We choose our coefficients to maximize this L, our likelihood. And this is not as easy that you can take the derivative and set something to 0. So this optimization, it has to be done iteratively. So, well, we just use R to do the calculation for us. And if you actually pay attention to this formulation, it's kind of like a binomial probability function. So that's exactly what we are going to do in this general linear model function in R. So this GLM function, and we specify the family equal to binomial. Well, for this default data set, predicting default use balance, our model would be like this. This is our formula, and you have to specify family equal to binomial so that you are fitting a regression model. It will still give you the coefficients, the estimates, and p-value for testing either your coefficients equal to 0 or not. So yeah, so this is how you do the estimation in R. And another important concept in logistic regression is called divines. If you recall, when we do the linear models, simple linear regression, multiple linear regression, we measure how well our model works in part by how close the data are to the model by looking at the residual sum squares. So we try to reduce the residual sum squares. But in logistic regression, the concept of this RSS is replaced by this divines. And this divines is defined as the difference of the log likelihood for the fitted value comparing to a perfect model called saturated model, which in the saturated model, it's manually assigned the probability of 0 and 1 based on the actual value of y. So this would give you, like each data point would have its own parameter, so-called parameter. So it's, you got so many parameters in this model, and it's you have to get like this perfect prediction. So it's called a saturated model. So this divines is the difference of this saturated model and this the log likelihood of your fitted model. And just like the RSS, we also want this divines to be small. This D is actually always larger or equal to 0 because the log likelihood of this perfect model would always be larger. And if it will be 0 for a perfect fit, which is this saturated model. So we want this divines D as small as possible. Okay, and a benchmark for evaluating the magnitude of the divines is called the null divines D0, which is when you fit the null model, which predicts a proportion of successful outcomes, just use the probability of success of your whole data set. So example here, if 1/5 of the outcome are default, then you just predicted the probability of being default given any balance would always be 1/5. So this is a null model. And with this, we can compute the corresponding R square, a generalized R square of the version from least square. So here in logistic regression, R square is defined as 1 over the D of your fitted model, the D over this non-divines. So this R square is no longer the percentage of variance explained by the logistic model, but it is a ratio indicating how close is the fit to be perfect, because we're using this divines here. This is important to know, R square in logistic regression. And we will definitely calculate the divines from R and do the comparison between models, use the value of divines, even do testing. So let's look at the summary of the output again from this logistic regression. We see that the estimate for beta 1, the coefficients of the balance, being 0.0055, this indicates that an increase in balance is associated with increase in the probability of default because it's a positive value, right? And 1 unit increase in balance is associated with increase in the log odds of the default by this much unit. Remember, this is the log odds because that's the new response you are fitting, right, with this linear model. And the testing is just the same as before, and we're actually testing Like for this one, we're testing null hypothesis being beta 1 equal to 0. It's the same saying that the probability of 1 does not depend on x. That's what that means, right? That's what this beta 1 equal to 0 means. So if that's the case, then the probability of x will be like this. So by looking at this p-value, which is really small, we reject the null hypothesis and conclude that there is an association between y and x, the probability of y and x. So this is how you interpret your result from logistic regression. Well, the next part will be prediction. Remember what we want to do prediction. With the coefficients calculated, we can compute the probability of default just by plug in the value we have. And for a balance of 100, 1000, this probability is 0.005 or 0.058. For a balance of 2000, plug in 2000 here, and we find the probability being 586. Well, what this tell us? We predict an individual with balance of 1000 has less than 1% chance of defaulting, and an individual with a balance of 2000 has a 58.6% chance. Dramatic, right? Meaning this balance have really a large impact on the probability of defaulting. Where we also saw from the plot, the box plots comparison in the very beginning. Well, we can also, like, if we have a qualitative predictor, like one of your predictor being a categorical or binary, we can still use the logistic regression to do the predictions. So the default data set has a variable called student. We code it to 1 if the person is a student and 0 if not. So we do this logistic regression of this default on student and still specify this binomial family so that we are doing a logistic regression. And now we got our estimates and the p-values for our tests. So now we have a binary predictor. If we want to compute the predicted probability of the default for students and non-students, we can just plug in, right? Where the only difference is that we're given the x value being either 1 or 0. Being 1 means it is a student, 0, that's not a student. And by comparing the probability of default, we can conclude that knowing an individual is a student increases the predicted probability of default. Note this is when the person is a student. This is not a student. Actually, the positive value of the coefficients. So this coefficients also tell us this being a student increase the probability default. Well, what we just talked about is just doing the logistic regression with one predictor, but we can also do this multiple logistic regression by including multiple predictors. So we have now still logit or log odds on the left-hand side, and on the right-hand side, you have this multiple linear regression type of model. You have x1 up to xp. And now we can rewrite this probability of x being like this, right? You just extend this to xp. And let's look at again with this default data, but do a multiple logistic regression. So we basically regress this default using income balance and the binary student variable. And from the estimates and the p-value, we can see that this student, like being a student or not, is negatively related to balance. Well, so knowing an individual as a student decrease the predicted probability of default. So earlier, like in the previous slides, the earlier slides, that we said it was positively related. So what is going on? Like when we do this multiple regression, we got like this different sign here. Well, you might guess it has problem of multicollinearity. Basically, those predictors are correlated. Well, I have this plot how to describe the situation, the phenomena. Or for a given balance, for example, let's just focus on this balance of 2000. The student's default rate, is below a non-student default rate. Oh, but before we go that, this orange is for orange lines are for student, and the blue are for non-student. So for a given balance, the default rate is this dashed lines. So, well, just a second. The student's default rate is below a non-student default rate. Oh, sorry. Yeah, we're looking at the default rate, which is this, well, the dashed line, what I'm looking at is the average, the overall balance and income. So this dashed line is for this bullet. And this curves here is for this bullet. The student's default rate is below for a given balance. Let's look at this 2000 and go up to look at this two lines. This non-student default rate is higher than the student default rate, right? Just go up here. This one is higher than this one. Well, the overall rate of student defaults, average overall balances and income would give you this comparison. So this orange is the students. The average, the overall default rate for students is actually higher than the overall average for non-students. So this is what's happening, like here. So why this happens, we mentioned this is because of the correlation. And if you look at their credit card balance and plot versus this student status, they are correlated, right? Like being a student tend to have a higher balance. Yeah, orange is student. Yeah. Student tends to have a higher balance, which is related, this higher balance related to the defaults, related to defaulting more than lower balances. So even though a student with a given balance has a lower probability of defaulting than a non-student with the same amount, but overall student defaults more than non-students. So this is what's happening. Well, you can look at this more closer. But why do we care about this correlations and the interpretations? Because this is really important for this credit card company, that when they are trying to determine who they should offer this credit. A student is riskier than non-student. If no information about the student credit card balance being available. But that student is less risky than a non-student with the same credit card balance. Right, the information matters. This is why including the correct variables is important. And this is telling us using a single predictor is sometimes risky, and like when you have other informations, it's better to get a balance of use more information when building the model. Well, this would be a perfect like study case for like industry related projects. It's very common that you get interview questions about like something like this. Well, we can also do multiple response classification. Like when we have a response, have multiple like classes. So we can still do logistic regression. And for example, for the blue, purple, and green example, and we can model this probability of Y being blue given X and probability of Y being purple, and then we can compute the remaining by doing this 1 minus this 2. Or in practice, this is not done very often, and for those scenarios, we would use other more advanced or just different classification methods. And we will talk about those in later chapters when we talk about classifications formally. And I believe this is the end of the slides. Yep. Okay, next we will talk about some R lab examples, and there are some more important informations there too. So see you in next video.